This tutorial is on the ionic product of water, which is a constant you use when calculating the pH of an alkaline solution. Now you can learn how to do this just by plugging values into equations, but by looking at the origins of the constant, what it really means, you can learn an awful lot of chemistry. So I've drawn a couple of water molecules here showing the electron pairs. I mean, I could just represent a water molecule like this if I wanted, but I'm showing all of the outer shell electrons because I want to show you how a water molecule can separate or dissociate to form ions, because in any body of water there will always be a tiny proportion of the water molecules that have undergone this dissociation. Now, although the chemical bonding in water is covalent, we've got electron pairs, shared electron pairs, this dissociation involves breaking the water molecules into ions. So the bond breaks between this hydrogen and the oxygen, but notice how the electron pair, the shared pair of electrons, stays with the oxygen. So over here is the hydrogen and here is the other oxygen with the other hydrogen attached. Now, because this hydrogen has left behind its electron, it's now a positively charged ion, and because this oxygen and hydrogen have got an extra electron, the one lost by the hydrogen, then it's a negative ion. So I hope you recognise that as being the hydroxide ion, which we can write simply as OH-. But very often you will see a pair of electrons shown on there, although there are 3 lone pairs of electrons on the hydroxide ion. Sometimes we just show this pair because they're the ones involved in the bond that was broken. Now the hydrogen ion, if you think about it, it is just a proton, so it's very small and a full positive charge. So it's got such a high charge density, a full positive charge in a tiny volume, that it would never exist in free solution. It always attaches itself to another water molecule by forming a dative covalent bond. So if I put the proton over here next to a second water molecule, I can use a curly arrow to show how a pair of electrons on here go to the hydrogen ion to form a new covalent bond. And it's called a dative bond because both of the electrons came from one of the atoms, the oxygen. So this is what we have. So those electrons now are the covalent bond to the hydrogen, but we still got a positive charge because in all of that there is an overall positive charge, so there must be in here. We've not added any electrons. This ion, I can represent it like this, showing the covalent bonds and just the single lone pair of electrons. And that's because once the dative covalent bond has been formed, it's indistinguishable from the other covalent bonds. Chemically exactly the same, just that the electrons both came from the oxygen rather than one from the oxygen and one from the hydrogen. So this ion is called the oxonium ion, or the hydronium ion, or the hydroxonium ion. I can just write its formula as H3O+, and just call it the oxonium ion. Now this process, it's called the auto-ionization of water, the spontaneous dissociation of water molecules into ions. And in doing this, water is acting as both an acid and a base. This water molecule, it's releasing a proton, so a proton donor is an acid, and this water molecule is acting as a proton acceptor. So it's acting as a base. I can write this out just as a single reaction. So here we've got the first water molecule Here's the second one, and we get the H3O plus and the OH minus. Now, in the reactions which follow the equations, I'm not going to represent the H plus ion as the oxonium ion. I'm just going to write H plus. So when you write H plus with a little aq, what you really mean is the oxonium ion, the H3O plus. And so I can simplify this reaction, and instead of showing both of the water molecules, I can just show one water molecule dissociating into a proton and a hydroxide ion, as long as we remember that this one forms a dative bond with a second water molecule. All I've really done is subtract one water molecule from each side of this reaction, and so that's a simpler way of representing the auto-ionization or dissociation of a H2O molecule into ions, a H plus ion and a hydroxide ion. Now, to emphasize the fact that only a very tiny proportion of the water molecules in any body of water have dissociated, I'm just going to put a very tiny arrow there and a longer arrow here, because of course this is a reversible reaction. A H plus combining with a hydroxide ion is what happens in neutralization. So it's a reversible reaction, but the equilibrium is a long way to the left hand side. The proportion of the water molecules in any body of water that's dissociated depends on the temperature, because for a H2O molecule to dissociate into H plus and OH minus ions, you have to break a chemical bond. And breaking chemical bonds requires energy. It's an endothermic process. So the higher the temperature, the more energy there is to break water molecules. So for example, at 25 degrees C, 298 Kelvin that is, the hydrogen ion concentration in pure water is 1 times 10 to the minus 7. 1 times 10 to the minus 7 moles per dm cubed. That just comes from the pH, and the pH of pure water at 25 degrees C is 7. pH equals 7, so if we do calculate the proton concentration, it's simply you reverse the sign of the pH, and that's the power to which you raise 10. And if the water is pure, then for every H2O molecule that dissociates, you also get a hydroxide ion. So there's a H2O molecule. If I dissociate it, I get one H plus ion and one hydroxide ion. So the concentration of the hydroxide ion is 1 times 10 to the minus 7 moles dm to the minus 3. Now that is for 25 degrees C. If, for example, you're at a higher temperature, let's just say at body temperature, 37 degrees C, then higher temperature, more of the water molecules have dissociated, so you get 1.5 times 10 to the minus 7 moles dm to minus 3 of each of these. And if you calculate the pH of that, it means pH would be 6.8. So when we say a solution is neutral, we mean an equal concentration of H plus ions and hydroxide ions. But neutral pH is 7 only at 25 degrees C. At body temperature, neutral pH is pH 6.8. At pH 6.8 we have equal concentrations of these, which just happens to be a bit higher. Similarly, at a lower temperature you have lower concentrations of these and a higher pH. I'll show you later how to do these calculations, but first of all I want to try and emphasize really how few of the H2O molecules are dissociated at at any temperature. Let's stick to 25 degrees C for the time being. You can see the concentration of water is of H plus ions is 1 times 10 to the minus 7 moles per decimeter cubed. What about the concentration of H2O? What is that? Well, it may seem unusual to be thinking about the concentration of water, but the concentration of anything is just written as moles dm to minus 3. Those are the units of concentration. What they mean is how many moles do you have in a decimeter cubed. So here is a decimeter cubed of water. The number of moles inside there will tell me the concentration of pure water. Okay, so to do that I need to first of all work out the number of moles, and the number of moles equals the mass of the substance in grams divided by the molar mass, and this has units of grams mole to the minus 1. Now you're probably used to just putting mass over mR, and that's just a bit of a hangover from GCSE. At A level you should really be using molar mass. First of all, mR, relative formula mass or molecular mass. Well, certainly molecular mass doesn't really apply to ionic substances because they don't occur as molecules. Molar mass covers everything, so it means the mass of 1 mole. So in the case of H2O, that is simply 18. So the relative formula mass of water is 18, but it doesn't have units if it's relative formula mass. It just means it's the mass compared with 1/12, the mass of an atom of carbon 12. But when we're using this as the molar mass, what we're saying is that if you have 18 grams of H2O, you're getting 1 mole. Okay, and so what we want to know is how many moles we have in a whole decimeter cubed. Now, what is the mass then of a decimeter cubed of water? And then we just write that on the top. Well, that's quite straightforward. 1 decimeter cubed is the same as 1,000 centimeters cubed. Now, it is unfortunate that the glassware that you use in the laboratories has the volume written in millilitres, ml, so that's 1,000 millilitres. But we shouldn't be using millilitres. It's not the appropriate unit. We should use centimetres cubed because the metre is the appropriate base unit. But a millilitre and a centimetre cubed happen to be exactly the same volume, so 1,000 millilitres is the same as 1,000 centimetres cubed. And so because we know that the mass of 1 centimetre cubed is 1 gram, if we've got 1,000 of them, which is a decimetre cubed, we know it must be 1,000 grams. So I can write 1,000 grams over here. It's 1,000 grams. And if I do the calculation, well, 1,000 divided by 18 is 55.6, just to 3 figures. And then if I look at my units, cancel them down, grams on the bottom, grams on the top, I'm left with moles to the minus 1 on the bottom. Mole minus 1. And if I move the units up to the top, then I change the sign, and what I get is 55.6 moles. So this is another reason why you should be using molar mass at A level, because by writing molar mass you're going to be using the appropriate units, and they serve as an internal check to your calculation. If the units don't cancel down and give the appropriate units at the end, you know you've done something wrong. So that this is giving me moles, which is what I was expecting for my units. So what I know now is that in that decimeter cubed of water, I have 55.6 moles of H2O molecules. So 55.6 moles in a decimeter cubed is 55 moles dm to the minus 3. I'll just write that up here. So the concentration here is 55.6 mole dm to the minus 3. Hopefully now then you can appreciate how few of the H2O molecules are dissociated. So in a whole decimeter cubed of water, I've got 55.6 moles of water molecules. So that's actually 55.6 times 6.02 times 10 to the 23. So that's 1 mole of water molecules. I've got 55.6 of those, so that's a very big number, but I've only got 1 times 10 to the minus 7 moles of H plus ions. Okay, now another way we can represent that is saying we have 1 times 10 to the minus 7 moles out of 55.6. I'll just do that on the calculator. 1 10 to the minus 7 divided by 55.6. Okay, that comes to 1.8 times 10 to the minus 9. But if I sort of scale that up by taking the reciprocal, it's like saying 1 in 556 million. Okay, so that's a little bit more meaningful. In that decimeter cubed of water, only 1 in 556 million water molecules have dissociated. So that's a very large excess of this one. Now this is dealing with pure water where you've got an equal concentration of H plus and OH minus, but supposing I add a small amount of acid to this, I'm going to increase the concentration of H plus ions. Well, what would happen is that the equilibrium would move to the left because some of the extra H plus would react with the OH minus and form water. But the concentration of water really wouldn't change at all. It's so large that making a few more water molecules by neutralising some H plus wouldn't change that. Similarly, if I added some hydroxide ions, some extra ones of these, a few of the water molecules would be used to neutralise them. A few of the H plus ions would be used to neutralise them. I'd make a few more water molecules, but it wouldn't change anything. So obviously we're dealing with an equilibrium situation here, so I can write an equilibrium expression for this. So for any reversible reaction you can define an equilibrium constant, and in this case it's the concentration of H plus multiplied by the concentration of hydroxide ions over the concentration of the intact H2O molecules. And always remember that these concentrations refer to the values when the system is at equilibrium. A little EQ there. Right, now saying that because this is such a large number and it's constant, then it's not going to change. So I'm going to just put it over here with this other constant. I'm just getting both of the constants at the same side of the equation. So I can do that on one line. Do it like this. So I've just cross multiplied, so I can put Kc, whatever that is, multiplied by the concentration of H2O is going to equal H plus multiplied by the concentration of the hydroxide ions. Now if you've got two constants and you multiply them, then you just make another constant. So why have two constants when you can have just one? And we call that constant Kw. and that is called the ionic product of water. So I'll just write that in the equation. So Kw, we call that the ionic product of water, and it's obtained by multiplying the concentration of H plus ions by the concentration of hydroxide ions, and it's temperature dependent, just like any other equilibrium constant. We've seen that the temperature determines the extent to which water molecules dissociate, and if we say that at a temperature of 25 degrees C, the concentration of water of H plus ions is 1 times 10 to the minus 7. Similarly, the concentration of hydroxide is 1 times 10 to the minus 7. So if we multiply those two together, then we get 1 times 10 to the minus 14. So when you multiply two numbers which have powers to the 10, you just add the minus 7 and minus 7, you get 10 to the minus 14. The units are moles squared. It's just like having moles to the 1, moles to the 1, and then dm to the minus 6. So the value of Kw at 25 degrees C is 1 times 10 to the minus 14 moles squared dm to the minus 6. And that is a constant. Remember, Kw, it's just a constant made of two constants. One is the equilibrium constant, the Kc, and the other is the concentration of water, which to all intents and purposes is a constant. So if I mess around with this equilibrium, supposing instead of having pure water, if I add a few protons, then what will happen is the protons will react with some hydroxide ions, reducing the concentration of the hydroxide ions until when you multiply them together they give Kw. So I can just put that one over here. We say 1 times 10 to the minus 14 moles squared dm to the minus 6. So at at 25 degrees C, the concentration of these two always has to equal this constant. So if I do increase the H plus by adding some acid, then the hydroxide ion has got to decrease in proportion, so that when you multiply these two together you get this constant. Similarly, if I add some alkali, increase the OH, some of it will react with the H plus, and the H plus will fall. That will fall a bit, but this will fall proportionately more until we reach this constant. Now the value of the Kw is temperature dependent. So for example, at 37 degrees C, which I mentioned earlier, it's got a value of 2.4 times 10 to the minus 14. So that's at 37 degrees C. So because if it's pure water, then H plus and OH minus are the same. So what I can just write is, where I see OH minus, I can just put H plus, which is the same as just H plus squared. So 2.4 times 10 to the minus 14 moles squared dm to the minus 6 is the square of the hydrogen ion concentration at 37 degrees C. So H plus becomes H plus equals 1.5 times 10 to the minus 7 moles dm to the minus 3, and as I showed you earlier, if you take the minus log to the base 10 of that, you get the pH, and the pH is 6.8. And that's the pH, the neutral pH, at 37 degrees C in pure water. The pH is 6.8, and you have equal concentrations of H plus and OH minus. Now the actual pH of the blood in in the body, arterial blood, is about 7.4. So this is an extension material really, but the pH of blood, pH equals 7.4 thereabouts, and if we're at 37 degrees C, we know that Kw equals 2.4 times 10 to the minus 14 moles squared dm to the minus 6. So we can write an expression here: 2.4 times 10 to the minus 14 moles squared dm to the minus 6. We're saying that equals the concentration of H plus times the concentration of OH minus. Now, because we know the pH is 7, then we can say that the H plus concentration is 10 raised to the power, where you reverse the sign of the pH. So if I just plug that into the calculator, so 10 to the minus 7.4, that's giving me 3.98. So I'll just call that 4 times 10 to the minus 8. Okay, 4 times 10 to the minus 8, and that's going to be moles dm to the minus 3. So we know the Kw value, we know the concentration of H plus ions from the pH. The one we don't know is the concentration of the hydroxide ions. So what I'm going to do is cross multiply, so I move that underneath here. So 4 times 10 to the minus 8 mole dm to the minus 3, that's going to equal the concentration of hydroxide ions. So I just work that out. So 2.4 10 to the minus 14 divided by 4 10 to the minus 8, it's going to give me OH minus concentration equals 6 times 10 to the minus 7. And again, you can, if you put the units in during your calculation, then they cancel out appropriately to give the correct units at the end. So that cancels out and that becomes minus 3. So moles dm to the minus 3. So let's just check that. The beauty of these calculations is you can always work them backwards, so to speak, to make sure you've got the right answer. So we're at pH 7.4, and at body temperature Kw is 2.4 times 10 to the minus 14. It's going to equal the hydrogen ion concentration, which I said, let me just calculate that again, it's 10 to the minus 7.4, so that comes at 4 times 10 to the minus 8. That was the H plus concentration, and if I multiply that by 6 times 10 to the minus 7, which is the, so this is H plus and this is OH minus, and you can see that they come to 2.4 times 10 to the minus 14. 4 lots of 6s is 24, and if you add the powers, then it comes to 2.4 times 10 to the minus 14. So that's, we always think of pH 7 as being neutral, and so but that's only the case at 25 degrees C, and at 37 degrees C neutrality is pH 6.8. So it means that in arterial blood, where the pH is 7.4 at 37 degrees C, it means we've got quite a large excess of hydroxide ions over H plus ions. That's 6 times 10 to the minus 7. That's 6 times 10 to the minus 8.